Welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Nikolai Matni, who is an assistant professor in the Department of Electrical and Systems Engineering at the University of Pennsylvania. There he is also a member of various other departments, among which the Department of Computer and Information Science, the GRASP Lab, the Precise Center, and the Applied Mathematics and Computational Science graduate group. These days he's also visiting faculty researcher at Google Brain Robotics in New York City. So something about Nikolai: he started his studies at the University of British Columbia, where he obtained his Bachelor of Science and Master of Science in Electrical Engineering. He then moved to better weather, where he obtained his PhD in Control and Dynamical Systems from Caltech in 2016. And then he spent some time as a postdoc at Berkeley and at Caltech. In general, his research interests encompass the using of learning, optimization, and control in the design and analysis of autonomous systems, with a lot of applications. For his work, he has received a large number of awards, which I listed in the bio. And today he's going to talk about what makes learning to control easy or hard. So I'm pretty excited to know the answer of this question, and therefore I'll leave you the stage. Nikolai, go ahead.
Awesome. Thank you so much for the intro, for the invitation. Really happy to be here today. While we certainly don't have a complete answer to this question, hopefully we'll have something interesting to say. So let me just get my slides up. Go. Okay, so this is part of this Autonomy Talks session or series of colloquiums, and a recent focus in this space has really been on that of safe autonomy, where folks are really worried about and really care about providing strong guarantees of safety and performance especially when starting to integrate learning-enabled components into safety-critical decision and control loops. So I think we've all at this point seen videos of robots falling over, self-driving cars running red lights or driving where they shouldn't be. I think we all appreciate that this is a very important and pressing engineering challenge right now. So what I would like to do is maybe start by motivating why we're thinking about this question from a slightly different perspective. One that might maybe speak a little bit more to the graduate students in the audience right now, which is this idea of graduate student dissent. I think we've all been there in one form or another, right? We come up with this fantastic idea, we go we had to try it ourselves or tell our advisor, and we start playing around with some code. And no matter what we do, nothing is coming out the way we want. We set a model to train overnight and the training curve looks pretty bad. So we do a hyperparameter sweep and things start to look a little bit better, but it doesn't quite get there. You keep tuning and things start to go haywire until after 2 weeks of tweaking with the different weights in your reward function, you start to have deep nightmares about these different training curves. Right, and so the question that we're really interested in kind of understanding here is why isn't this working, right? Deep learning and deep reinforcement learning in particular, they're notoriously finicky in terms of their sensitivity to hyperparameter tuning and data collection and things like that. So one of the fundamental questions we'd like to understand is, what scenario are we in the sense of, is it that we are in a setting where if I get some more compute and explore even more different types of hyperparameter choices, I'll eventually end up converging to something that works well? That's one category of problems. And the other category of problems would be where I'm in a setting where things are just fundamentally hard, in the sense that even if I get my hands on the best possible policy for the task that I'm trying, I'm still going to just have really bad reward, really bad performance. And I think what's really challenging and what I think leads to a lot of frustration both in academia and industry is the fact that right now we really don't have a systematic way of disambiguating these two scenarios. We can't really tell a priori or after a little bit of experimentation, am I in a setting where the problem is just fundamentally hard, or do I just need to spend a little bit more time with hyperparameter tuning? So to try to come at a more principled answer to this question, we looked for inspiration from a field that actually is able to disambiguate these two kinds of scenarios, but when there's no learning involved. And so this is the field of robust control. Now, I'm sure a lot of folks in the audience, when they hear robust control, they think of something like H infinity. And while that's certainly, arguably the most famous result from robust control, I would argue that the most practically important contribution of robust control to engineering overall has really more been the identification of these fundamental limits of control, right? And what these essentially tell you is that for some systems, it doesn't matter what controller you deploy, you're going to have just really, really bad performance. A favorite example of my PhD advisor, and I like to use this example in classes and talks as well, is this idea of balancing a stick on your hand using vision. So this is something that you can try at home if you have one of those old school extendable pointers. And what's nice about this setup is that we can write down a simplified model for it and actually identify analytically the fundamental limits of control. So in particular, through a little bit of analysis, we can identify that the unstable pole of this system is dictated by the length of the stick. And so in particular, if the stick gets shorter, it becomes a lot harder to balance. And again, if you try this at home, you'll see that that's the case. And we can also show that we introduce an unstable zero if we start introducing, what I'm going to call bad sensing. In particular, if suppose your stick is quite long and you put something like a baseball cap on so you can only look at the middle of the stick, then this introduces an unstable zero. And what we know from robust control theory is that if this unstable pole is close to this unstable zero, then we're starting to lose controllability of this unstable mode. And so again, if you try this at home, you'll see that if you have a long stick and you look at it near the base with a baseball cap on, it becomes almost impossible to balance because essentially we're amplifying, what you end up doing is amplifying the noise in your depth estimation from vision in a really undesirable way. Okay, so suppose that you identify a system that suffers from these poor fundamental limits. What does this mean? Do you just throw up your hands and give up and go home? No, of course not, right? What you do is you close a co-design loop and you change the system, right? So in this toy example, if you're in this unstable pole, unstable zero cancellation setting, what this means is you have bad sensing and you need better sensors. And you can imagine a more involved version of this with more sophisticated systems, where again, you identify the bottlenecks of control and then modify the system to circumvent them. So what I'm going to talk to you about today is some work that we've been doing in my group and with collaborators to try to take these ideas and these concepts and bring them over into the data-driven learning-enabled setting. And at a high informal level, the question that we're trying to understand is what makes learning controllers from dynamic data easy or hard? Right, so dynamic data is key here. We're not getting IID rollouts. We're actually IID samples from the system. Things are correlated, so we need to take that into account. And the informal meta theorem that we've been converging towards is essentially one that you would hope to see, which says that good optimal controllers are easy to learn and bad optimal controllers are hard to learn. So in particular, if you're in some scenario where you're doing all of this hyperparameter tuning and no matter what you do, you're seeing tons of variance in your loss function or your gradient estimate or whatever, this could be indicative, this could be a signal that the underlying control problem that you're trying to solve is itself ill-posed, and you need to actually go back and modify the system. What we've also done is identify a class of systems or some conditions that your system needs to satisfy, or sufficient conditions, so that actually learning a controller is easy. And so this is what we're calling good optimal controllers. And we'll give you examples today of both of these settings. So the plan for the rest of the talk is first we're going to start with some negative results, kind of get the bad news out of the way first. And we're going to talk about what makes learning controllers hard. And we'll start by digging a little bit deeper into existing positive results for linear systems and try to identify what they can in some cases actually be hiding. Because we've had a bevy of positive results for learning linear systems over the past few years, but it's important to understand when and where they're still limited. And then we'll see some examples of what I'm going to try to convince you of are actually practically relevant linear systems that can still be hard to control. once we've gotten the bad news out of the way, we'll switch things over and we'll start thinking about what makes learning in controllers easy. We'll use imitation learning as a case study to try to tease apart what properties of the underlying data generating system we want to have satisfied. And in particular, what we're going to focus on is how you can deal with distribution shift from training to test time in imitation learning through the use of a precise concept of nonlinear robust stability. And then we'll wrap things up. Okay, so let's dive into thinking about learning to control linear systems. So just to set the stage, we're going to be considering for this first part, for the most part, just a simple state feedback scenario. So I have a setting where my system state is described by x of t at time t. This A matrix here describes the autonomous dynamics of my system when I'm hands-off. And U of t enters through this matrix B, and this is the actuation. This is what I get to apply to my system. And we have this external disturbance, which could be stochastic or adversarial, or anything in between that kind of is making our life difficult, and we're trying to basically control our system towards the origin in face of this disturbance. And so in particular, most of what we're going to talk about today is focused on LQR optimal control. There are many reasons for this that I'm happy to discuss offline, but the overall problem is this idea that I want to minimize the steady state variance of my state and actuation. So the assumption here is that our disturbance is stochastic. And potentially also the policy that I'm playing pi, if I set u of t equal to pi of xt, there might also be some randomness in there, and we'll see why we might want to do that later. And I'm going to try to convince you, and this is really what the whole learning for dynamics and control community has argued for the past 4 or 5 years, those focusing on linear systems, is that although linear systems are not perfect representations of reality, they're fairly ubiquitous, and both linear systems and LQR are useful benchmarks in the sense that because of this nice linearity, they're still simple enough to analyze, but they're still somewhat general enough to capture not all, but some very interesting and rich behaviors. Okay, so this is the general setup. This is kind of the overall problem that we're going to be thinking about. And as I mentioned, we're going to assume, unless I specify otherwise, that we have access to the state x of t when we're trying to compute our control action. And so, I mentioned earlier that there are a lot of positive results in terms of learning to control linear systems. So one might look at them and immediately think, there's not much left to do here. Learning to control linear systems is easy. We're going to consider 2 distinct but related tasks. One, we're going to think of an offline task, and then we're going to think of this as the sample complexity of stabilization. So in this context, the problem setup is, a simple version of the problem statement would be, I'm given an unknown system. So I'm given an unknown system, and I want to find a feedback policy, u equals to kx, such that the resulting closed loop system is stable. And I get to compute this k using data generated from my system, so sequences of state and input trajectories. And over the last 4 or 5 years, there's been a really rich body of literature showing how you can do this. And in particular, we end up with these pack bounds, which basically say that with probability at least 1 minus delta, so with high probability, if I have enough data, and importantly here, enough data means polynomial in the underlying size of my system, then I can find you a controller that is in fact stabilizing. Right, so kind of going, one of the earlier papers that I worked on in this space was looking at exactly this problem from a robust control perspective, and since then, lots of folks have built on this idea. So in terms of offline stabilization, if you look at the literature, you would be very much inclined to say, okay, this is easy in the computational complexity sense, in that I only need to collect polynomial amounts of data, and the types of algorithms underlying this are things like least squares, so nothing super complicated on the computational side either. So that's the offline sample complexity, the offline problem. We're also going to think about an online task. So you can think of this as an adaptive control problem, and we're going to characterize quantitatively the behavior of an adaptive algorithm through regret bounds. So in this context, I'm again given an unknown system, potentially with an initial stabilizing control policy, and our goal is to minimize this regret. And this regret is essentially the running sum of what I compute of what my system is seeing, and we're comparing this to a baseline that is essentially scaling with the optimal cost, had I known the true dynamics of the system. Right, and so you can imagine that if I can show that this regret as I run it is sublinear in t, then if I take an average, this decays to 0, which tells me that my adaptive controller is indeed converging towards the optimal controller. And not only that, the bounds give me a rate at which this happens. And so if you look at the literature again, going all the way back to the seminal paper from Yasin and Chaba, what you see is that with probability at least 1 minus delta, you can bound this regret with a square root in t. So if I divide that by t, this goes away. So that's nice. That's called sublinear. And again, importantly, we have that this problem regret scales polynomially in the underlying state dimension of my system. Okay, so if you put all of this together and you were to just look at this, this would tell you from a complexity analysis perspective that learning to control a linear system, both in terms of offline stabilization or online adaptive control, is easy. These are all polynomial complexity. So what so I'm obviously going to poke some holes in this in some settings, because otherwise I wouldn't really have a whole lot to talk about. So let's dig into just a couple representative results in both of these spaces to see what they may or may not be hiding. And so I'm going to pick on one of my own papers for the offline sample complexity, the sample complexity of offline stabilization. So in this original paper, what we showed was that if you essentially used a least squares type of system identification problem approach, and then combined it with a robust control method that takes into account the uncertainty in your estimates, you can show that you can get a stabilizing controller if n scales like the number of states plus the number of control inputs divided by the minimum eigenvalue of essentially the controllability matrix of this system, where we consider both control and noise as inputs. Similar looking results exist, for example, in regret bounds for LQR. This is what I would consider the latest kind of state of the art in this space from my former lab mate Max Simchowitz and his collaborator Dylan Foster. And there they show that greedy exploration, so just injecting a little bit of noise along with your control action, plus least squares plus certainty equivalent control, which means I just take my estimates as given, leads to this order optimal regret. Now, what I want to highlight is these two control theoretic quantities. I have on one, in the offline stabilization setting, we have this minimum eigenvalue of my controllability gramian. And in the regret setting, we have this upper bound that scales with the norm of the Riccati of the Riccati recursion matrix, which we all know corresponds in some sense to a cost to go for this problem. So the question that we want to understand here is, what potentially are these control theoretic quantities hiding? Right? There's this implicit assumption in all of these results that these control theoretic quantities are somehow independent, do not scale with the underlying size of my system. And so I think the first result that really looked at this question in earnest was from my colleagues here at Penn. So Tassos is now a postdoc at ETH, actually, with John Lederos. So Tassos and George looked at this problem in the context of just system identification. So they considered an autonomous system, no control input, but in contrast to previous work, they allowed for degenerate noise. Right? So rather than having the process noise directly excite every mode of my system, perhaps it only enters through certain states. And what they were able to show is that you can actually construct interesting systems. And I'll explain in the next couple of slides what interesting is. But for now, just think of this as we're eliminating the obvious pathological cases that would cause problems, for which this minimum controllability, the minimum eigenvalue of my controllability gramian is exponentially small. So what this tells me, in other words, is that if I want to actually get an accurate estimate of this system, I need to collect exponentially many data points where the exponent scales with the underlying dimension of my system. So this was a first kind of blow to this idea that learning to control linear systems is always easy. But this doesn't necessarily tell us that learning to control is actually hard, right? Because it may very well be that I don't actually need to learn everything about my system to stabilize it. It could be that this is a very, inconsequential mode that if I applied model reduction, I would just throw away. Or it doesn't necessarily mean that I actually need to identify every part of my system if I want to do good, let's say, online adaptive control. Okay, so those of you in the audience who have more of a control theory background, you're probably thinking, well, the controllability of my system obviously has to play a role here, and you're absolutely right. But we're going to have to look at the controllability of our system from a slightly more refined perspective. So just to make sure that everybody is on the same page, if I have my original linear time invariant system defined by an A and B matrix, then the system is said to be controllable if this controllability matrix here has full column rank, full row rank, that's a typo, for some k less than or equal to m, the size of the size of the state dimension. Now, if you've taken a robust control class, you know controllability is not enough. And here's a very simple example showing you that controllability is not enough to be able to learn to control a system or identify a system. So here's a really toy example. The bottom state has no dynamics, but it's basically a one-time step memory for the control input, and there's a very weak coupling there's a potentially weak coupling alpha between the second state and the first state, which just integrates it. And so you can look at this, and with a little bit of thought, you should be able to convince yourself that the sample complexity of actually identifying this A matrix with the 1 and the alpha goes to infinity as alpha goes to 0, because I'm allowed to excite the system less and less and less as alpha gets smaller and smaller, but there's still this noise term here that's hitting the first mode. But I'm controllable for all alpha not equal to 0. So what this tells us is that we need to look at the controllability gradient. And we already saw that the controllability gradient popped up in a few of the previous upper bounds that we saw. So more explicitly, an implicit assumption in all of the previous work that we've seen is that this minimum eigenvalue of my controllability gradient is polynomial in my state dimension. So what I want to show you next is a class of systems for which this assumption breaks, but it's a class of systems that is not pathological. It avoids this kind of simple, silly example that I have on the slide. And that's going to be this notion of robustly coupled systems. And I promise this is going to be the worst math slide of the talk, and you won't have to remember a whole lot from it. And so what I need to do is introduce this notion of staircase or Hessenberg form. And what this tells you is that if your dynamical system AB is controllable, then there exists a unitary matrix U such that if I apply this matrix as a state transformation, I'm able to reshape the dynamics of my system to look like this. And the key thing here is what this is doing is it's restructuring things so that the first state is basically all of the state that I can directly actuate. And then everything else is coupled in this kind of block lower triangular form. And then the other important thing is this notion kappa, which is the controllability index of the system. And basically you can think of this as the time to achieve controllability. And so the key takeaway here is we're going to define a class of mu robustly coupled systems, which basically says that both B1 and all of these circled A, A21, A32, et cetera, they're all at least mu big. So we're eliminating this pathological case on the previous slide where I can make the coupling between directly controllable and not directly controllable modes arbitrarily small. We're bounding all of those away from mu. So on the previous slide, that example, alpha would only be allowed to get as small as mu. Okay, so this is the class of systems that we're going to consider going forward. Again, the only thing to remember here is we've kind of set this up in such a way that mu corresponds to the coupling between modes in my system. And so the first result that we have is we can show that there are actually classes of mu robustly coupled systems for which learning to stabilize the system can be hard. So again, our setup, just to make sure that everyone's on the same page, we're going to assume that we have this time to controllability, this controllability index. And we're going to define that for our class of systems. And the class of systems we're going to consider are those that are mu far away from being uncontrollable, in the sense that to make it uncontrollable, I would have to take one of these coupling elements and subtract off mu worth of coupling. And so our hardness result looks something like this. All of these hardness results, they're built on these ideas of information theoretic lower bounds. And what it states is that for any algorithm, the sample complexity to actually find a stabilizing controller over this class of mu robustly coupled systems scales exponentially in the controllability index kappa. So if we can come up with such a hard instance, such an instance where kappa here, this controllability index, is actually the same size as my state dimension, then we have something that's exponentially hard to stabilize. Rather than diving deep into the nitty-gritty of the proof, I think it's instructive to look at an example of such a hard instance. So, these hard instances, essentially, they reduce to a two-point hypothesis test. You present two systems that you argue are very hard to disambiguate from each other. And this, in some sense, leads to these hardness results or lower bounds. And so the systems that we're going to consider, they consist of a single marginally stable mode at the top, and they're coupled via a chain of basically mu integrators, so my control input comes in directly at the bottom, has gain mu, and then kind of goes up this chain of mu coupling up until it hits the top mode. Now, if you look at this and you stare at this a little bit, you should be able to convince yourself that a necessary condition for any learned controller k hat to stabilize this system is that the first entry in that controller needs to be the opposite sign of this first entry here, right? So what this tells us is that to stabilize this system, I have to actually perform system identification on that first term that's blue, right? I have to determine whether it's plus or minus mu. Now, the problem, though, is that this is hard to identify because any excitation that I introduce through this through my control input goes through this chain of n-1, through this chain of n-1 mu dampings. So I have exponentially small excitation. So this gives you an example of how essentially, if you can reduce the stabilization problem to a sys-ID bottleneck, in this case, identifying whether the sign of this first blue term is plus or minus, then this can lead to hard stabilization problems. Right, so I know this looks like a little bit of a contrived example, but you can actually construct other examples that have non-zeros along the diagonal. And essentially what this is telling you is that if you have a chain of damped single integrators, right, and this could pop up, for example, if you're, I don't know, discretizing a TDE to do like soft robot control, or if you have like a snake robot, or if you're controlling a chain of coupled systems, then this could actually lead to problems in terms of system identification and consequently stabilization. Okay, so that's for the offline stabilization setting, but that doesn't necessarily tell us that once I actually have a initial stabilizing controller, that adaptive control is hard. And what we'll see interestingly now is that the adaptive control problem can also be made hard, but the instances that are challenging are in some sense the opposite as the one that I just showed you. So again, we're going to consider systems that have a defined time to controllability, which again, you should think of in terms of how many time steps I need for my controllability matrix to become full rank. We're going to consider these mu far away from controllable systems. And for technical reasons, we need to consider this a dilation around them of radius epsilon, but this radius epsilon can be arbitrarily small. And so what we show is, again, using these information theoretic bounds, is that for any policy pi, this policy can inject excitation, it can do whatever it wants. You again end up in a scenario where your regret is now lower bounded by something exponential in the controllability index of your system. And again, I think what gives the most intuition or the most instructive thing is to look at an example of a hard instance that's used to prove this result. And so for this case, the system that we consider is one that is basically two decoupled systems. The first system has no dynamics. It's just a direct control input. And then the second subsystem, which is decoupled, is just a chain of integrators, a chain of integrators. Right? We're assuming in this case no degeneracy in the noise. The noise directly activates every mode. And so the structure of this problem, because the optimal controller because the dynamics are decoupled, the optimal controller is decoupled as well. And what we consider are a class of perturbed systems inspired by this beautiful geometric argument from Polderman from the late 70s, where we perturb our system in the following way. We add a delta to the true B, and we subtract off the effect of delta K star on the true A. And the key feature of this construction is that for both A tilde and B tilde in A and B, the resulting closed loop dynamics under the optimal policy are the same. And what this means is that if I can pick a delta that is not too small, but leads to A tilde and B tilde looking similar, which we can do, then this means that I actually need to explore away from the optimal policy to be able to identify the true dynamics of my system to actually be able to converge to the optimal controller. But for this system and other systems like it, this system is exponentially sensitive to exploration. And you can see that due to the chain of integrators here, right? When I introduce some exploration into this control input, it gets amplified and integrated all the way up. And so we're suffering an exponential hit in our performance and hence regret because some modes are too easy to accept. Right, so you end up with this really interesting kind of contrast where for stabilization, what gets you into trouble are these sys-ID bottlenecks that are hard to excite, whereas in the context of adaptive control, it's the opposite. You get into trouble if you have modes that are too sensitive to your exploration. And what this tells you is that if you're trying to do both, what you really want is a system that kind of sits in between. You don't want any modes that are super excitable or super damped. And in fact, if you look at the literature, at the kinds of examples that people run these systems on, that's typically what they tend to look like. Okay. So I just want to briefly mention that we can also extend these ideas to policy gradient methods for LQR, which don't really fit neatly into either of the two categories that I just discussed. Right, so again, LQR optimal control, as we've been considering it, as we're minimizing this quadratic cost, this expected variance of the state and control input, subject to these linear dynamics. Now, you can also, rather than trying to identify the A and B matrices and do some control based off of that, you can imagine running a stochastic policy gradient method instead, where, for example, I would update my current policy k-hat by taking a gradient step in some direction that's an estimate of the true gradient of my cost with respect to my controller. Right, so so here I'm using jk of s to denote the cost of my system under the contemplated policy k, and this hat here is an estimate of this gradient. And so this work was the first really beautiful paper to show that this actually works for LQR, which was a surprising result because the overall landscape here is in fact not convex in the controller gain K, was by Miriam Fazl and Miriam Musbahi and Sham Kukad, and I think I'm forgetting an author, Wrong Du maybe, from Washington and Duke. It was a beautiful result. And they showed that this work, leveraging ideas from gradient domination, this actually works, and it has polynomial complexity, both in estimating getting an estimate of your gradient as well as converging to the optimal controller. So one thing that we want to try to understand was, do these same kinds of ideas of hard to control systems pop up in the context of policy gradient? And so what we decided to use as a measure of hardness was the variance of this gradient estimator. And we defined this notion of d epsilon local minimax complexity to really kind of zero in on instance-specific local difficulties in terms of estimating this gradient. So in particular, we ask that our algorithm needs to perform well on any epsilon perturbation of my nominal system. And we're only looking at the gradient estimate in a vicinity of the optimal controller, right? So we're really kind of giving this gradient estimate the benefit of the doubt here. We're not saying it has to be globally accurate. It just needs to be globally accurate on a small ball around the nominal system and in the vicinity of the optimal controller. You know, if your algorithm cannot give you a good estimate there, you're pretty much hopeless. And what's cool is we can actually take those same ideas that I showed you from the adaptive control problem and bring them into this picture. So a hard instance looks something like this, which is, again, very similar to the problem that we saw for adaptive LQR. We have a decoupled system. We have two decoupled systems, one with no dynamics, one that's a chain of integrators. To make this problem a little bit more interesting, we have to define an input budget. And what we can show, again, is that this minimax local complexity is exponential in the state dimension. And this is done using exactly the same construction as above, where, again, you could maybe, sorry, not as above, but as previously shown, where the idea here is that to get a better estimate of my gradient, I have to excite the system a little bit. I have to do some local exploration. And this is a system that is very sensitive to local exploration. And so what this tells me is that if some modes are too easy to excite, then this could also lead to large variance in my estimates of my gradient. So in our paper, we also extend this analysis to partially observed systems. I'm not actually going to show you the theory, but I'll show you actually an empirical study that actually we did that predates and in some sense inspired some of this work, where we took this original example that I described earlier of this kind of balancing an inverted pendulum with your finger, with your hand, and we implemented it in PyBullet. And so the way that we simulated this idea of having restricted vision to only being able to look at the middle of the stick was we used this black, this black bit at the top here is what's obfuscated or what's blocked from the vision controller. So on the left here, you can see vision and you can see depth. And we trained both state, depth, and image-based controllers using reinforcement learning. And what was really cool was we saw this very clear trend in terms of the amount of episodes and the variance in terms of this reinforcement learning algorithm, in terms of achieving higher reward, that was entirely consistent with the results that we later were able to prove, and were entirely consistent with what robust control predicted. Okay, so as a takeaway, if we kind of zoom out a little bit, we first started thinking about what makes learning controllers from data hard. And what we've seen is that systems that are either too excitable or not excitable enough have controllers that are hard to learn. Right, so it's really kind of, you want to, if you're designing a system for which you have to both do sysid, stabilization, and online adaptive control, you really want to try to hit this sweet spot where you have something that isn't too excitable, or you don't have modes that are either too excitable or not excitable. Okay, so we've gotten the bad news out of the way. Let's move on to some good news. What makes learning controllers easy? And as mentioned, what we're going to talk about, what we're going to use as a case study to try to make some progress in answering this question, is imitation learning. So let's make sure that everybody's on the same page in terms of what we mean by imitation learning. The basic setup of imitation learning looks something like this. I have an expert policy, sitting up here, and I deploy this expert policy on my system of interest. This leads to a collection of data. You can think of these as labeled pairs. I have my state and the corresponding label of the expert's control input. And I feed this data into a regression problem. This is just typically some form of supervised learning where I try to learn an approximate policy pi hat that matches the actions pi star on my given data. And the most vanilla version of imitation learning, which is called behavior cloning, that's essentially it. I get my pi hat out and I deploy it on my system, and I hope for the best. Now, people really like to use imitation learning as opposed to reinforcement learning when they can, because when it works, it's much more sample efficient than reinforcement learning. Now, I emphasize when they can, because imitation learning doesn't always work. And in particular, the big challenge related to getting imitation learning to work in practice is this idea of distribution shifts. Now I can apply, standard fancy statistical learning theoretic tools to give me generalization bounds on the supervised learning problem. The issue, though, is that those supervised learning bounds are only with respect to data generated by my expert policy. But I don't actually really care about pi hat generalizing well on expert data. I need pi hat to generalize well on data generated by pi hat. But I don't have pi hat until after I've solved the regression problem. So it leads to this kind of chicken and egg problem. Maybe taking a look at this, we can look at this from maybe a little bit of a cartoon perspective. If I think of these arrows here as my expert trajectory, and this cloud here is a cartoon version of my expert distribution, then if I run this problem and I get an estimate pi hat, and now I try a test point initial condition at this black dot. Now my expert will take this step in the blue direction. There's a little bit of error in my learned policy pi hat, so I end up over here. Again, my expert knows what to do, and I'm still within my training distribution, my expert distribution, so I only make a small error again. Unfortunately, this compounding of small errors has now kicked me outside of my training distribution. So whereas my expert presumably still knows what to do, I may make an even bigger error because I haven't seen this kind of data during training. This kicks me further out of my training distribution, which leads to potentially an even bigger error and failure. Right? This is a well-recognized issue of covariateship and cascading failure that appears in imitation learning. This has been addressed by a wide range of techniques within that community, and I'll give a brief overview of those on the next slide. But our interest in this question, in this problem, was really to try to take a more dynamics and control perspective on it, and to try to understand how the underlying, say, stability, safety, smoothness properties, et cetera, of my underlying expert affect the sample complexity in terms of how much data I need to collect to make sure that this catastrophic failure that's on the slide here doesn't actually happen. Okay, so as I mentioned, what I showed you on the previous slide was this idea of vanilla behavior cloning being sensitive to covariateship. Now, there exists some standard approaches in the literature for dealing with this. If you have something that's called an interactive expert oracle, or you can think of this as an on-policy approach, something like Dagger has been very successful. So the idea there is you let your learned policy run, and when it starts to veer a little bit too far off course, you let the expert correct you. And then you take this new data and fold it back into your original data and resolve. And the idea there is you're essentially teaching your policy to how to recover from the errors it's likely to make at test time. Another approach is the off-policy approach, which assumes that you don't have access to this online query, that you can't query your expert online. And the idea there is, in various different ways, you inject noise into the data collection process. So you actually perturb your expert data while it's being generated to, in some sense, preemptively puff out the training distribution, so that you hope that when you make errors at test time, you still lie within the training distribution that has been artificially puffed out via this injection of noise. Now, the key idea, if you kind of just zoom out a little bit and think about what's going on in all of these algorithms, is you're trying to show your learned policy how to recover from errors, right? Either by perturbing your expert and letting it recover, or by letting the expert take over once you've made some errors. Now, there's an implicit assumption in all of these works that, as far as I'm aware, has never been crisply articulated. And this implicit assumption is that my expert can actually recover from errors, right? So if you think of these off-policy things where I'm injecting noise while I'm collecting data, if my expert was so fragile that when I injected this noise, it failed, that would not be a good expert, right? So we're always assuming somewhere here that my expert actually knows how to recover from these errors. Another word, another terminology for recovering from errors is robustness, right? So our goal here was really to try to make the assumption explicit and understand the role of robustness in experts in terms of the sample complexity of imitation learning. When does it work? When doesn't it? How can we make it work when it fails? So with that in mind, let's dig a little bit deeper into what a candidate imitation learning formalism might look like. So we're going to consider deterministic nonlinear dynamical systems. No real assumption on the underlying structure. The only randomness in our system is going to be through the initial conditions. So we're going to be drawing initial conditions at random. We're going to assume that our control input takes a form, the following form. One is the policy that I'm playing, and then we're also going to have this input perturbation term. For now, we're going to keep it general, but just think down the road, we're going to use this input perturbation to capture our learning error, the difference between our learn policy pi hat and the expert policy pi star. And so the imitation learning problem can be summarized in some sense in terms of trying to bound this imitation gap, which looks at the maximum over my trajectory of the distance between the state of my test trajectory and my expert trajectory, both starting from the same initial condition. Right? Another way of saying this is that I have good imitation learning if I can guarantee that my learned policy would stay in some tube around the expert policy's behavior for the same initial condition. This, in some sense, prevents this catastrophic failure if this tube is not exponential, for example. I'm also going to apologize that the notation is maybe a little bit heavy here, but the key thing to remember is the superscript pi or pi star corresponds to the actual policy that we're playing to generate the data, and phi sub t corresponds to the state of my system under that policy starting from an initial condition, and the argument here would correspond to the potential sequence of perturbations. Again, I get that it's a lot, but unfortunately, we actually need to keep track of all of this. But again, whenever it's important, I'll do my best to remind you of why it's important and where. So our first, I'm not even going to call it an insight, but our first step to tackling this problem is to write our test policies as perturbed experts. Right, so I have my test policy on the left here, and it's being applied to a state generated by my test policy. I'm going to rewrite this as my expert policy, again, applied to the state generated by my test policy, because that's what's actually being deployed on the system, plus this delta term. Right, and this delta term just captures the mismatch between my learned policy and the expert policy on the test trajectories. And so just rewriting the imitation gap above in this new language, I can rewrite the imitation gap as the difference between a perturbed expert trajectory and a nominal expert trajectory. Right, and this is why we introduced all of this annoying notation, was to get ourselves to this point. Right, because in particular, we know how to deal with bounding the gap between perturbed and nominal trajectories in nonlinear control. And that's formalized to this notion of incremental input to state stability. So for those of you with a nonlinear control background, I will put up the formal definition here, but I'm going to pictorially try to explain to you what this is encoding. Incremental input to state stability, or what I'm going to call delta ISS going forward, asks two conditions of your system. One is that if my system has no input perturbations, has no disturbances, then it forgets its initial conditions. So all trajectories eventually look the same. And then the other idea is that if I have if both trajectories start from the same initial condition, but I perturb one, then bounded perturbations have a bounded effect. And not only that, but we can actually quantify this bounded effect in terms of this class K infinity function gamma, which you should just think of as a growth rate or an attenuation rate in terms of how well my system either amplifies or attenuates input perturbations. Now, for the imitation learning problem, since we assume that all of our all the trajectories we're comparing start from the same initial condition, we really only need this bounded disturbances have bounded effect notion. And in fact, we only need it to happen locally. So for those of you who want to know more about that, happy to talk about it offline or point you to the paper. But this is the key idea that we're going to use. And it turns out that if you assume that your underlying expert system satisfies this notion of input to state stability, incremental input to state stability, then you can actually bound the imitation gap in terms of gamma, this measure of attenuation of my closed loop system, as applied to the worst error between my learned and expert policy on the test data. Okay, so I'm just going to recopy that here, and I'm going to highlight both what's good and what's bad about this. What's good is that it explicitly captures the effect of expert robustness on the imitation gap. right? So if gamma is, let's say, very small in a precise sense, that I'll make precise in a bit, then my system shouldn't be sensitive to these errors. But the challenge here is that the argument is, in fact, in terms of the policy mismatch under my test policy pi. I don't have access to this when I'm doing training or when I'm or during training or during analysis. And this is what's challenging. So we came up with an adversarial criterion for generalization, which we can state as follows. We asked that my expert policy pi star is approximately equal to my test policy pi. And what's nice about this is it is defined in terms of the expert trajectories, right? Notice that there's a pi star up here. So this is the data that we have access to during training, but we need for it to hold not just along the expert data, but in a tube around it. And the size of this tube is related to, and how small this error needs to be is related to the underlying robustness of our system. But if you can show that this holds true for a given expert trajectory, then we can guarantee that this leads to a small imitation gap. And so this is going to be our underlying approach for dealing with this chicken and egg problem of going from expert data to test time generalization. The challenging thing about this adversarial criterion, though, is it's not an easy thing to optimize, right? You have this nested max, and you would want to minimize the worst case version of this. Now, while you may potentially be able to tackle this directly in special cases, we suggested an alternative approach based on the Taylor series. And the basic idea here is we take this policy mismatch under the test policy pi, and we do a Taylor series expansion about the expert data. So we've now upper bounded our policy mismatch on the test data in terms of the policy mismatch on the expert data, a term that depends on the Jacobian of the policy mismatch under the expert data, and the imitation gap. So this is nice because we can use statistical learning theory to bound the policy mismatch under expert pi star. This is stuff that I could just analyze using standard tools from supervised learning. The issue, though, is that the imitation gap now appears on both sides, right? So I end up with this implicit bound. What's nice, though, is that we actually, so I did a first order Taylor series expansion. Here you can do generalized versions of this. But what's nice here is that we actually are able to, through learning, make these terms underlined in blue as small as possible. So potentially, if we make these things small enough, this leads to a non-vacuous bound. So I want to give you a couple of examples of when this actually holds true by instantiating specific examples of robustness in our expert. So one case is if this gamma of x, this thing that captures the amplification or attenuation of disturbances on our expert, is quadratic. So you should think of quadratic as super robust, right? If you think of x less than 1, this is attenuating things really aggressively. So if I assume I have a very robust expert, and that all of my policies are Lipschitz, then we can show that a small policy mismatch on the expert data leads to a small imitation gap. What this means is that if I have a very, very robust expert, behavior cloning will work every time, right? And so we're excited to identify this because this does, in some sense, identify a class of systems for which behavior cloning will work. And we have seen in practice that behavior cloning, when it does work, works really, really well. Now, perhaps a more generally applicable system, class of systems is ones for which my gamma of x decays linearly. So for example, if you have a control affine system that is locally stable around trajectories, it will satisfy this. So if I assume I have a slightly less robust expert, and in some sense, because I have the slightly less robust expert, then I need to assume a little bit more about the smoothness of my policies. So here I'm going to assume C2 policies. In this case, we can show that if we bound both the behavior cloning loss, the policy mismatch, as well as the Jacobian loss. So I make sure that the Jacobian of my learned expert and policy, my learned policy and expert are close, then this guarantees that I can bound my imitation gap in terms of the behavior cloning loss on expert data. So to summarize this, what this tells me is that if I have sublinear decay, then if I do behavior and what I'm going to call Jacobian cloning, this will work. And we can generalize all of this into what we call tassel or Taylor series imitation learning. This paper just won the NeurIPS lottery, so it'll show up at NeurIPS this year. And the idea here is that to ensure robustness to distribution shift from training to test time, what you want to do is make sure that the pth order Taylor series of learned and expert policies match. Right, so we can define a corresponding tassel loss that matches from the 0th up to pth derivative of our system and define a corresponding empirical risk minimization problem. And so the two examples that I've shown you previously are instantiations of this. So for very robust experts, behavior cloning works. For slightly less robust experts, behavior cloning and Jacobian cloning works. And you can expand this as you change the rate of decay of gamma of x. And we can put this together into a nice learning theoretic theorem that tells you that if you collect enough data, where enough data is emphatically determined by the underlying robustness properties of your system, then you can guarantee small you can guarantee small imitation gap. So let me just wrap up real quick with some examples, some experiments of this. First, a synthetic experiment where we constructed a system where we could actually explicitly show that our expert satisfied these notions of incremental delta ISS with a particular exponent in the attenuation. And so what I'm showing you here are both the imitation gap and the mean policy discrepancy. The blue curves correspond to just behavior cloning. The orange curves correspond to behavior cloning plus Jacobian, and the green are behavior, Jacobian, and Hessian. And the way to read these plots is from the left, I have a smaller exponent, and so these are less robust. And as I go to the right, my exponent gets bigger, which means a more robust system. And what you can see is that there is a outsized effect or difference between the different orders of my behavior cloning for the less robust systems, but this difference goes away as my system becomes more and more robust, which is consistent with our theory. Now, of course, you also want to see things that are not just these toy examples. So we looked at Mujoko, and we kind of ordered these informally from more robust to less robust. And what's also cool about this algorithm is it's not really an algorithm, right? It's just an additional loss term. So we could tack it onto vanilla behavior cloning. We could tack it onto an offline approach like Dart or an online approach like Dagger, and we see benefits in all cases. So, I'll look at two extremes, right? Let's focus at this upper left corner here, which is the swimmer. The swimmer is as robust a system as you could hope for. It is this thing that's wiggling around on the ground, and not only that, it's in viscous fluid, right? So you see that there's really no difference between behavior cloning and the behavior cloning plus a Jacobian loss term. Now, however, if we go and look at, let's say, half cheetah or humanoid, which are slightly less robust systems, you can see a significant win in terms of just adding this Jacobian term to the loss. And this holds true for all of the other algorithms as well. So I'll just show you a video of what this looks like as well. So these policies were trained using just 12 trajectories of 100 data points each. And so you can see that the top row is just traditional behavior cloning, whereas the bottom row is behavior cloning plus a 1 tassel loss. So you can see even for the humanoid, the very high dimensional system, with a little bit of data, we're able to learn something that works quite well very quickly. Okay, so in the interest of time, I'll skip this slide, but we also have some additional results showing that incremental stability leads to easy learning in other contexts. If you're interested, please let me know. I'm happy to share these results with you. And I also had this fun new result with work from Google, where we use similar tassel-inspired ideas, this idea of needing to show a policy how to recover from error to inform how to collect data for teleoperation from teleoperators for offline reinforcement learning and imitation learning. And in the interest of time, I'm going to skip that, but if you're interested, I'm happy to share it with you. The TLDR is that you need to show both failure and recovery to actually be able to do well in this context, which is very consistent with the results that we saw from the theoretical analysis that I just showed. Okay, so if we kind of zoom back out, and I'm just right on the hour here, to summarize, right, we started off by asking this question of what makes learning controllers from dynamic data easy or hard? our informal meta theorem was good controllers are easy to learn, bad controllers are hard to learn. So what we just shown was that in the context of imitation learning, a good controller is one that leads to an incrementally robustly stable system. And we saw that for linear systems, if I have modes that are too excitable or not excitable enough, they can get you into trouble. So I'd like to just very quickly thank my amazing collaborators. The top row of folks were collaborated on the first half of the talk, the bottom row, the second half. And I just want to end with a plug for L4DC, which we'll be hosting at Penn next summer. It's going to be really cool. We have an awesome venue lined up. Penn in the summer in June is beautiful. So the submission deadline is November 18th. Please send us your best papers. It's going to be fun. All righty. Thank you so much, everybody. I'm sorry I went a little bit over time, but more than happy to take any questions should you have any.
Thank you, Nikolai, for the great talk, and no problem, we have time. So let's open the stage for questions. You can ask your question by raising the hand, and I will call you. Or even you can write on the chat, and I can read the question for you. So I received a personal message for a question, was referring to the first part of the talk and was asking whether the results were holding also for time varying systems. So this is a linear systems analysis.
Yeah, that's a great question. So, I mean, the perhaps not fantastic answer to that is that linear time invariant systems are special cases of LTV systems. So they naturally carry over, right? So, there's going to be a subclass of LTI systems within LTV that are provably hard. So in that sense, it does carry over. But I've had this question pop up in different in different contexts. So I've also been asked, like, what about nonlinear control? And I think in both contexts, the interesting thing there will be to define a class of systems for which the linear results don't just carry over directly, right? So for example, for nonlinear systems, you could look at a local linearization and essentially carry things over, maybe modulo some error control analysis. For LTV systems, well, LTR are a special class of it. So an interesting question is, would LTV mod LTI lead to hard problems? It's not clear a priori, right? Because perhaps the changing dynamics will introduce some excitation, but there would need to be some kind of regularity just to be able to meaningfully define what an LTV sys-ID problem looks like. So I think these are great questions. I don't have, beyond these kind of obvious extensions, I don't have a good answer to it, but I think it's something worth looking at.
Great, thank you. Any other question? Don't see any raised hands. Actually, you didn't have time to go through it, but I was curious about these applications you were working on with Google. So you skipped this nice video, and maybe, I don't know, I can use my question time to let you show it. And
it's a 3-minute video. If you don't mind, I'm happy to show it.
Absolutely,
it's a really nice video my colleagues put together. So I figured that the video does a much better job than I could, so I figured I'll just let it go.
This video presents visual backtracking teleoperation.
You guys can hear the audio? Good.
Standard practice when learning from teleoperated data is to collect successful demonstrations of the teleoperator completing the desired task. This video shows such a dataset collected with our teleoperation setup on a UR5 arm performing a deformable t-shirt grasping task with randomizations in lighting and background clutter. Unfortunately, a policy trained on just successful demonstrations will not be able to recover from mistakes that take it outside of the training data distribution. In our deformable grasping task, this causes failures like the one seen here, where the arm continues to lift even though it has missed the grasp. To resolve this issue while remaining completely offline, our VBT method includes failures and recoveries as well as successes into the dataset. As seen in this simple grid world example, VBT data provides coverage of failure to reach the rightmost room and recovery from that mistake. In general, collecting a VBT trajectory takes 3 steps: failure, recovery, and success. VBT can be applied to any sparse reward task that is amenable to teleoperation with well-defined failure modes. Here we demonstrate some VBT trajectories on our grasping task. Note that it is very important that failures and successes are collected within the same episode to ensure that they are visually similar. This avoids spurious correlations that may arise from changes in non-relevant visual details like the background. To evaluate VBT, we collect 4 datasets on our real robot grasping setup, each containing only 1 hour of data, success, containing only successful demonstrations, VBT, which is our method, coverage plus success, a dataset that is 50% failures and recoveries and 50% successes. But unlike VBT, failures and successes are collected in distinct episodes so that they are not visually similar. LFP plus success, a dataset that is 50% play data and 50% successes. VBT data facilitates more accurate learned Q functions. Here we visualize a held out trajectory that is not present in any training set. The trajectory contains a missed grasp, followed by recovery, and then success. When we visualize a Q function trained on success data, the values continue to rise after the grasp is missed, and only drop when the gripper is opened. This is inaccurate and gives unjustifiably high values to states where the gripper is closed without the shirt in hand. The same issue persists when we mix in visually distinct failures with the coverage plus success or LFP plus success datasets. In contrast, when we train on VBT data, the learned Q function correctly indicates that the value drops precisely when the grasp misses and not when the gripper reopens. VBT data also leads to better policies. This table shows the result of a large A/B test between a variety of policies trained on different datasets. The main finding is that training IQL, an offline RL algorithm, on VBT data outperforms all baselines. Moreover, policies trained with VBT data demonstrate learned recovery behaviors. Thanks for watching.
Yeah, so what I thought was really cool about this result was that you really did need to show the learn policy how to not just identify a failure but also recover from it, which is very much kind of in the spirit of the work that we were doing. And what I thought was really striking was kind of how it's only with those kinds of data that the Q function learns how to change in the right way on a missed grasp. And there were some really interesting kind of engineering challenges here because we were using kind of mechanical Turk type workers to do the teleop. And so we couldn't estimate the Jacobian of a teleoperator. So we had to come up with other ways of trying to do it. But it still kind of shows this idea that you really need to encode not just failure, but also recovery into your data sets.
That's very interesting. Thank you. In the meanwhile, I don't see other questions popping up. So it means that the talk was very clear, and also maybe
or I lost everybody, but
maybe they are processing. It's one of the two. But thank you very much again, Nikolai. It was a great having you. Good luck for the next steps.
Yeah, thank you so much. And I just also want to add that all of our code is open source on GitHub. We're always eager to help out collaborators, either just help you get the code up running or to work with you. So if you're interested in any of what we discussed, please feel free to reach out to either me or my students. All right, thanks everyone.
That's great. Thank you very much. Enjoy the rest of the day. Bye.